do you get when you take the theory of general relativity and combine it with the principle of supersymmetry? You get supergravity. Today, we'll be exploring a class of theories that attempts to unify two of the most clashing frameworks in physics, gravity and quantum field theory, in the attempts to pave a way towards a possible theory of quantum gravity. But first, let's talk supersymmetry. The principle of supersymmetry states that for every bosonic field, there is a corresponding supersymmetric fermionic field, and vice versa. The number of supersymmetric partners a field has is governed by the supersymmetric charge, which we will denote by n. For simplicity, we will take n to be 1 and work in 4 spacetime dimensions. Given a bosonic field B and a fermionic field F, we can vary the fields with respect to a supersymmetry parameter, which we will call epsilon, to switch between the fields. By varying the bosonic field with respect to this parameter, we get the fermionic field, and by varying the fermionic field, we get something that is proportional to a translation in the bosonic field. It should be noted that epsilon is a spinor-valued function, so as to conserve the spin or helicity of the fields. If we take the commutator of two supersymmetric variations, we get a new supersymmetric operator. By acting on it on the bosonic field, we get something that is proportional to its spacetime derivative. Thus, any theory that is invariant under supersymmetry will necessarily be invariant under translations. In fact, supersymmetry is an extension of Poincare symmetry, thus this result is not surprising. Now suppose that the supersymmetric parameter depends locally on the points of our spacetime. The supersymmetric variations don't get altered too much, but now the action of the commutator operator becomes proportional to a spacetime dependent vector field. This vector field in fact belongs to the infinitesimal version of the group of diffeomorphisms of the spacetime. So, any theory that's invariant under local supersymmetry is also invariant under diffeomorphisms. This means that in such a theory, the metric itself needs to be a dynamical object. The simplest theory with a dynamical metric that emits a supersymmetric extension is Einstein's theory of general relativity. But before we move on to that, we need to take a closer look at what it means to go from a theory with global symmetry invariance to one with local symmetry invariance. Consider a simple Lagrangian of a complex scalar field phi. This Lagrangian is invariant under global U1 transformations. Such transformations are of the following form, where the field is shifted by some phase factor. Now let alpha depend locally on the points of our spacetime. We now have to introduce a covariant derivative with a connection being some vector function which couples to the field. This is a gauge field, or rather the more familiar electromagnetic gauge field. Our Lagrangian is no longer invariant under local U1 transformations, so we have to change it to include the newly introduced gauge field. This procedure is referred to as minimal coupling. To make the Lagrangian fully invariant, we have to include an additional kinetic term which describes the dynamics of the gauge field, the familiar Maxwell's electromagnetic Lagrangian term. Now the new Lagrangian is fully invariant under local U1 symmetry. So we began with a scalar field of spin 0, and when making the symmetry local, we introduced a gauge field of spin or helicity 1. Our supersymmetric parameter is of spin 1/2, so in this case we will introduce a gauge field of spin 3/2. This is the so-called gravitino field, the supersymmetric partner of the graviton field. Notice how the field has both vector indices and spinor indices. Right, so here's the setup. We're going to be working within the framework of minimal supergravity. This means that we only have one supersymmetric partner for the gravitational field. We will be trying to write down a supersymmetric Lagrangian that describes the graviton field and the gravitino field. To help us, we will need to formulate our theory in terms of tetrads. In the end, we will have a supersymmetric Lagrangian that looks a little bit like this. As is known, the Einstein-Hilbert Lagrangian is the kinetic term for the graviton field. Let us define a new auxiliary field which has both Lorentz indices and spacetime indices, as well as a local dependence on the spacetime. This object is known as the tetrad field. The tetrad can be used to connect the metric tensor to the flat Minkowski metric. Tetrads will be useful for getting spinors coupled onto curved spacetime. We now define a new type of derivative, called the Lorentz covariant derivative. This is given in terms of an object called a spin connection, and the generators of the Lorentz group, since tetrads are defined up to local Lorentz transformations. This ensures Lorentz invariance. By imposing the condition that the tetrad field is covariantly constant, we get a set of equations that uniquely determine the spin connection. In addition, we can define the so-called spin curvature and show that this is related to the Riemann curvature and the inverse tetrad fields. We can now rewrite the kinetic term of the graviton field in terms of the tetrad fields, using the definition of the spin curvature we established earlier. Notice how here we have the determinant of the tetrad, which makes sense since the tetrad field can be thought as the square root of the metric tensor field. Now the following Lagrangian gives the kinetic term for the gravitino field. Here epsilon is a totally antisymmetric tensor density and gamma nu is the local Dirac matrix on curved space. This is the so-called Rarita-Schwinger Lagrangian, which describes the dynamics of a spin 3/2 field. We can now put everything together to arrive at our supergravity Lagrangian. To make this fully symmetric under local supersymmetry, we must also include a term that is at least of order 4 in the gravitino field. Now we are ready to proceed with the analysis. The calculations are quite long, so we will not go any further, but an enthusiastic viewer can use the following supersymmetry transformations to try and determine the precise form for the additional Lagrangian term. Additionally, this basic setup allows us to begin introducing ideas such as matter coupling, which I encourage you to do. We only covered the very basics of supergravity, but I hope that this introduction has given you some insight into the vast and exciting subject. Supergravity theories have been formulated for higher supersymmetric charges, dubbed extended supergravities, and it has been known for quite some time that higher dimensional supergravities manifest themselves as lower energy limits of string theory. In 2019, the discoverers of supergravity were awarded the Breakthrough Prize in Fundamental Physics for their discoveries. Perhaps supergravity holds the key to one day finding the highly sought-after theory of quantum gravity.